Welcome, everybody. Welcome back from lunch. Thank you so much for getting back promptly for this. And thank you for joining us for a romp through the world of quantum, is what I'm calling it. I'm Joseph Lorenzo Hall. I'm from the Internet Society. For our sight-impaired audience, I'm about 6'3", 230-pound white man, no hair with a beard. Sitting next to me is Simson Garfinkel, who I'll introduce in a sec, who has a lot of hair and no beard. Simpson is a fellow of the AAAS, the ACM, and the IEEE, and he holds a PhD in computer science from MIT and a Master of Science in Journalism from Columbia University, which you heard mentioned earlier today. I remember Simpson as a computer scientist I met in grad school who, like me, was slightly obsessed with research ethics and things like institutional review boards, which is not what computer scientists tend to talk about until you get in trouble with one of them. But we're here to talk about quantum technologies and a recent book from Simpson and his co-author, who some of you might know, Chris Hoofnagle. It's called The Law and Policy for the Quantum Age. This is available via open access. You can go download it right now. I encourage you. It's a really good book from Cambridge University Press with a recent Audible version that's abridged, so it's not the whole entire thing, and spoken by a fantastic voiceover artist, or voice artist. But first, we want to sort of get a feel of the room. How much do you all know about quantum technologies? Can I get a show of hands if you know the difference between quantum cryptography and quantum cryptanalysis? Can I get a show of hands if you know the difference between quantum sensing, quantum computing, and quantum communications? Okay, it looks like...
What is entanglement? Raise your hand if you feel comfortable with entanglement.
Spooky action at a distance. Gosh. Clearly, we'll have to do a little bit of level setting. What should these folks know before we launch into... What we'll do is do a little bit of discussion of what you should know, and then we'll talk about myths and facts. So we're going to tend to talk to each other since the lights are so bright. But
they're really bright. So
this is a fire.
So the fire is a good example of a quantum process, right? Like the whole reason that we can see it is that these electrons are being stimulated and then they're relaxing. They're getting stimulated from the heat, and when they relax, they let off light at different frequencies. And that's a quantum phenomena. But that's not the kind of quantum phenomena that is used for quantum computing. That is quantum physics, but quantum computing is based on this idea of entanglement, which is making the system not make a decision about whether the cat's going to be alive or dead, to use the Schrodinger analogy. Like when you measure a quantum process, that determines something about the quantum process. And the way the quantum computers work is they prepare a whole bunch of qubits, which are these bits that are in superposition, and then a whole bunch of gates are sent to the qubits while they're all in superposition. And then we measure the qubits and we see what are the most likely results. And that operation is typically repeated thousands and thousands of times to get a distribution of possible answers. And that's how a quantum computer briefly works. So
gates are sent to the qubit? That
yes,
sounds a little different than normal computers.
It's completely different. Like, so with our normal computers, for those of you who are into architecture, the code is in memory and data is in memory, and we bring memory into the CPU, which is this fast arithmetic logical unit, and then we change some gates and we do some math and we send it back out to memory. But with quantum, the bits stay in the core, and the program gets played through the bits, or the qubits. Now, you've heard a lot about qubits, like they can store so much data. That doesn't really matter, because when you measure them, they're either a 1 or a 0. We hear things that there are these two big algorithms that was the real reason that the world became interested in quantum computing. So the idea of quantum computing dates back really to 1981. Richard Feynman gave a talk at a conference talking about, we could have a computer based on quantum properties and use that to simulate quantum interactions. But a guy named Peter Shor came up with an algorithm that would run on this hypothetical computer that could be used for factoring, and it could factor in polynomial time rather than in exponential time, which is what we're dealing with now. And that would make it much easier to crack RSA encryption. It also cracks elliptical curve encryption. And there was another algorithm that was used for search space. It basically gives you a square root speed up of the ability of searching, not through a database, but searching for a correct answer, like the particular AES key that decrypts this message. And that's Grover's algorithm. And so it effectively turns AES 128 into AES 64, and it effectively turns AES 256 into AES 128. So if you want to protect your data against these machines that might exist in the future, the first thing is you should be using AES 256, because there's really no penalty now for using AES 256 over AES 128. And even with Grover's algorithm, AES 128, it can't be cracked for the conceivable lifetime of humanity. With RSA, the feeling is that you should move to algorithms that can't be cracked by Shor's algorithm. So the National Security Agency has been looking at other public key encryption algorithms that would be resistant to Shor's algorithm, that are not susceptible to this attack. And they've come up with several, and there's a standardization process happening. And that's all based on the idea of being able to do computation with superposition.
Using qubits, right?
These are qubits, but you might say, well, we want 3 bits, so they're called qtrits, or with D levels, it's qdits. So these machines that have just a few qubits might be scaled up relatively quickly to have more states. That's research. And that's one of the fears, right? Today's machines have hundreds of noisy qubits, but in the future, we might suddenly have machines with thousands or tens of thousands of noisy qubits. Noise means that when you do that computation, you don't always even get the correct quantum answer. The noise kills the superposition, and the calculation just doesn't happen. And that's a problem. Or you get something very, very wrong, and so there's this idea of using quantum error correction. That the details always matter, and they're always different for the different machines. The sense right now is that to simulate the thousands of qubits that you would need to crack an RSA key, you'd need between 10 and 20 million noisy qubits.
Wow, that seems like a lot. I was just reading in IEEE Spectrum a short article about IBM's plan for the year, which sounds like it includes building more noisy qubits, building a smaller amount of less noisy qubits, and then connecting groups of qubits together to create a bigger...
Right, and so a few years ago, Google published this article that to crack a RSA key, like the keys we're using today, 8 hours on a machine with 20 million qubits that you can keep in superposition for 8 hours. So you have to have so little noise that it's not going to quench in 8 hours. But maybe the way you build that machine is you have 1,000 qubits and you connect 20,000 of those machines together with a quantum network. So what quantum networking allows you to do is it allows you to connect 2 computers together, they're quantum computers, and have them share that superposition. You can think of quantum networking as flying qubits. I didn't make that up. That somebody much smarter than me made that up. And a quantum network that only transmits 1 qubit or 2 qubits is quantum cryptography. And we've had working quantum crypto systems since the early 2000s. They allow 2 parties to agree on basically a one-time pad, that they get a sequence of ones and zeros that mathematically, provably, to our understanding of quantum physics, nobody else in the universe can share. These systems do not provide authentication, so most of the quantum cryptography systems actually use something like Diffie-Hellman or RSA on top of it to authenticate the stream. That's okay, because you're authenticating it in real time. And if somebody actually had a quantum computer and captured your authentication stream, they could decrypt it in 20, 30 years whenever those machines are available. It doesn't matter. The quantum encryption is very popular in some places, but the U.S. National Security Agency has said it's not needed in the United States.
No. And one of the things that was pretty remarkable in your book was specifically thinking about the promise for quantum computers and in physics simulation and designing drugs and catalysts and things like that. Do you want to talk a little bit about sort of where the near-term promise might be?
Yeah. So in the near term, quantum computers are good for one thing, and that is getting papers published in prestigious scientific journals. The second thing that they're reasonably good at, but we don't know for how much longer, is they're reasonably good at getting funding. But we may be heading towards a quantum winter if these machines don't pay off. If you remember AI winter, we went through 2 of those before AI really blossomed. And the same thing could easily happen on the quantum stage. But the actual useful applications that we know will work once we have a machine that's big enough is Feynman's idea of using quantum machines to simulate physics and chemistry. And we call those machines quantum simulators, which is a bad name, but I didn't make it up. And because quantum simulators also means we're simulating quantum computers with conventional computers, you can download Python code that will do that. And the other useful application is optimization. We now have some proofs that quantum optimization is provably better than some of our current optimization techniques. So with a large-scale quantum computer, you could do certain optimizations that take longer on classical computers.
And before we get to the 5 myths, in the book, one of the things that really struck me was of quantum sensing, of quantum computing, of quantum communications. Quantum sensing was where you and Chris came out saying, this is what you're going to see. This is what you need to be thinking about. This is actually required before you can do those other things. Can you talk a little bit about quantum sensing?
So who here has had an MRI? All right, so every one of you has been inside a large-scale quantum sensor. And if you think about what MRIs are doing, it's pretty phenomenal. They can look inside your body in 3D and distinguish one kind of atom from another kind of atom. That's magic, right? It's not like X-rays where they're passing photons, dangerous cancer-causing photons through your body and looking at how many get through. MRIs are doing something else, and what they're doing is they're looking at the spin changes on electrons that are floating around the nuclei that matter. When I learned MRI, we called it NMR, nuclear magnetic resonance, but we had to get rid of that nuclear word to make people accept it in the outside world because they, no radiation, but it's nuclear.
I was going to say, when I was in an MRI, I remember the problem set from my Berkeley graduate quantum class on nuclear magnetic resonance, and it was twice the nightmare.
So we have the story of the first MRI in the book, and it's funny that the lab where they developed it, they were sure it was going to work, but the question was who's going to be the test subject. So normally you would use a dead pig or something, but they put a graduate student in the machine. They did. They were going to put the faculty member in, but the faculty member had too much fat, and the early machine didn't work very well through all those layers of fat. So it's fun, but that technology has only been out since the 70s. So, we're nearing on a little more than 50 years. But we've been using quantum sensing for a long time. Another application of quantum sensing are atomic clocks. So quantum sensing makes precise time possible. And if you have precise time and you have a constellation of satellites going around the planet, you can get time and position. And then there's the sense of maybe building machines that can do dead reckoning with quantum sensing. So we're going to begin to see these payoffs that are well, we have been seeing these payoffs with quantum sensing, and they're going to get better, like technology that can literally see through walls instead of seeing through people. Or really precise measuring of reflected photons, distinguishing photons that you sent because they're entangled, and photons that you didn't send because they're not entangled with your source. And that's called quantum radar. And there was a lot of excitement about using quantum radar to defeat stealth. And if I knew anything about that, I couldn't talk about it. So.
Well, and if someone in the Slack wouldn't mind, there's a Twitter thread where someone describes all the sensing packages in the HIMARS multiple launching rocket system that we've sent to Ukraine. And there's quite a bit of tech in there, one of which is a ring laser, which you mentioned in passing, which is essentially a laser that's shooting in a circle, triangle, whatever, and it can tell based on orientation exactly where it is with unbelievable precision, and those are in each one of those things. So there's a lot of military applications.
Yeah, and one of my big surprises in working on the book was that you can now order ring lasers from China for a few, $50 to $100 or a few $100s. But yeah, basically, yeah, it's 3 mirrors and a laser, and it looks at the change in interference patterns as it slowly rotates to the left or to the right, clockwise or counterclockwise. Because the photons don't rotate, but the mirrors are rotating. And even though the photons are moving really, really fast. Now remember, photons aren't actually moving. They're just probability waves in a complex wave space. And they don't really exist until you sense them.
Photons
but nothing does, right? Like, we don't exist. We're just probability functions in a complex number space.
I had a physics professor who said photons are two-dimensional things that we travel through.
That's another way of thinking about them, yeah.
Okay. So let's get into these myths and facts.
Absolutely.
So myth 1, humankind is at the precipice of inventing large-scale quantum computers.
Yeah, when people say large-scale quantum computers, you
10 million.
have to ask them, what do you mean by that, right? So a lot of these physics simulations could be done with machines with thousands of noisy qubits. You just keep running the equations, and you look and you get a distribution of results, because with cryptography, there's only one correct result with cryptanalysis. But with sensing, with trying to model chemical reactions, you're okay with that distribution. So the National Academies put out a report, and they sensed that they said in the report a few years, like 3 to 5 years, till we have machines that are quantum simulators. And I think that in the IEEE publication, that's the current issue, I think, the machines that IBM is bringing out are either good enough to begin to do quantum simulation, or like 1 generation short, 2 generations short of being able to do that. And it depends on what you want to simulate too, right?
These are hundreds or thousands of qubits, right?
These are hundreds to thousands, not hundreds of thousands.
No.
Yeah.
Okay.
So, but if by large scale you mean something big enough to crack an RSA key, what do you mean humanity is on the precipice, right? On geological time, we certainly are. In terms of the duration of the Republic, sure, but in our lifetimes, maybe some of the younger people in the audience, I could be surprised, right? We could discover that a new algorithm has been invented for factoring tomorrow. Some organization somewhere on the planet might have a better algorithm for factoring today. So let's just work that out for 25 seconds. Pretend that there's some organization that employs a lot of mathematicians and they don't speak English, which has come up with a better way for factoring on classical computers. Maybe all their work on quantum has given them insight to better ways to factor on classical machines. So that organization now has a problem, right? Because it means that they can decrypt messages that they've recorded, But what can they do with that information? Because if they start revealing that information, then they lose their advantage because people realize what they can do. This is the same conundrum that the English faced in World War II when they could decrypt the Enigma, but they couldn't actually operationalize much of the intelligence from being able to decrypt Enigma because they didn't want to be able to reveal that they could decrypt Enigma. So it's a problem. So some organization might be able to do that now. We think it's unlikely just because organizations have a real hard time maintaining secrets.
Yeah, and even the IEEE article was pointing to IBM having, in the network case, maybe 2,000 or 3,000 qubits by 2025 or 2026. And that does seem maybe not geological, but very slow.
I don't even know how many of these machines IBM has. And we don't know what IBM has working. We only know what IBM has chosen to reveal.
Yeah. Okay. Myth 2. Quantum computers can try all solutions at once.
Yeah, it turns out that's not the way they work. If they did, then they would be, non-deterministic computers that could solve NP-hard problems by exploring the entire state space. But that's just not the way they work. Many people have described them as working that way, but they don't. Sorry.
You can't throw infinity gates at this qubit.
Well, what would be super cool, right? Like the way, if you believed in the many worlds hypothesis of quantum mechanics, which is that every time there's a choice, the universe forks. So there's like a really large number of universes, and we just happen to be in the particular universe where all these decisions were made. I do not believe in the many worlds hypothesis, but it's completely valid because there's no way to disprove it.
Yeah, I love things we can't prove.
Yeah.
So myth 3, all encryption will be unscrambled when quantum computing arrives. It'll be like a light switch.
Yeah. So let's drill deep on that one now. That the Google paper, which I highly recommend, says that if they had their 20 million noisy qubits that they could keep in superposition for 8 hours, they would get one encryption key, right? So you could crack one signing key, and then you could distribute kernel updates that look like they were properly signed. But if the threat model that people are concerned with is some foreign adversary recording all of our conversations, and like every Zoom connection, every voice over IP communication, every web page that gets downloaded, recording them all, having them in some big database, and then being able to decide which of those conversations to decrypt on this machine that takes 8 hours per key. Well, the first problem is you have this prioritization problem. You have this deconfliction problem. You don't want to spend your resources on something that you don't need to do. You have this targeting problem because it's really hard to distinguish each of those conversations and figure out which is the correct one. So even as it's the case now that like we don't use 64-bit encryption because it can be cracked, realistically, it's hard to crack 64-bit encryption. It's not just something you can do on your iPad in a second. So there's some security, but for national security, we're afraid.
And
they are afraid.
You need to get access to the encrypted communications, and so.
Oh, that's easy.
Yeah.
So yeah, like it's going through the air, right? Just set up some listening posts.
Large facilities in Utah that maybe.
No, they record it. But if you want to set up a listening post, who doesn't have a listening post in their pocket, right? It's just a question of recording the stuff that's going through the air. Yeah. But recording, storing it for an extended period of time, now you're talking about money.
So, myth 4. Quantum cryptography and quantum communications will be invulnerable to attack.
Yeah, so I mentioned that there are, in fact, commercial products out there that do quantum cryptography. You run it over a fiber optic. You can get 100 kilometers, I think, and we have a shared key stream that we can use. In practice, we will use that shared key stream to encrypt a link encryptor. We're going to make it our AES 256 key, and we're going to change that key every 5 seconds. And that is what commercial equipment will do for you today. So why don't we recommend those things? Or why doesn't NSA recommend those things? Well, they might be vulnerable to side channel attacks. That's hard to defend against, and we don't know if those machines are good at that. We know from many people who do this kind of thing, they say it's much easier to go around the encryption. So if you can get like an implant on your iPad, then we don't need to crack the encryption keys, right? And there are companies that sell implants for your iPad commercially to law enforcement. So we should assume that everything on your iPad is being sent to some organization other than Apple.
Makes me think of Post-it notes that say "decrypt here," which is about 10 years ago we started learning about.
There's a lot of options for getting around encryption, and just as with quantum cryptography, you have to get around the encryption because you can't crack that stream.
Okay, myth 5. America is at the head of the pack in quantum technologies.
Yeah.
And how much do we actually know?
Yeah, so who here thinks that the U.S. is ahead of the pack in quantum? So nobody here believes that. There's so many other countries out there working on it, like China. And then the U.S. programs are all basically multinational programs, right? So Google has a program, Alphabet, and Microsoft has a program, and IBM has a program, but they're all multinational teams. It's really just the Chinese that have a national team, and other countries that have unannounced programs that might be there. So. If I was going to build, advise a rogue nation, do they want to build a quantum computer or build an atomic bomb? I would, of course, say build an atomic bomb because it's much easier to do, right? Like that's 1940s technology. So
yeah, absolutely.
Think about that. Like nuclear weapons are 1940s technology. That's kind of cool. Go ahead.
I was going to say there's still some difficulties in separating isotopes.
Actually, it's gotten really easy.
Yeah. Compared to quantum computing.
And you don't have to, right? So this was the big breakthrough. So we researched a lot about nuclear weapons on this book because one of the hypotheses is that the difference between chemical-based weapons and quantum-based weapons, nuclear bombs, is similar to what we're going to have with this difference between classical computers and quantum computers, and that there's this technology transformation story that with quantum, the first machine that you build, the first working machine, is fantastically expensive. And then you spend the next 10 to 20 years lowering the cost of building those machines. And then once you've got the cost down to a reasonable basis, you can blast out as many as you want. And that's what we did with nuclear weapons. And that's what we did with MRI machines. And it's probably what's going to happen with quantum computers. The first machines are going to be the first useful machines. They're still going to be very expensive. And then we're going to work in getting that cost down. Now, in terms of isotopes, right, that we have two kinds of bombs. We have the bombs that use uranium and the bombs that use plutonium. Not talking about dirty bombs here, right? So getting plutonium out of the atomic pile is easy. You just have an atomic pile with some uranium, and it makes plutonium for you. And then you use chemistry, and you remove the plutonium from the uranium. And that was the first bomb that we blew up. And we knew that would work because, the math is easier. It's the, no, excuse me, I'm sorry, I have it reversed. We didn't have a lot of plutonium, so we had to work on the uranium separation, and that's harder to get right, but the bomb is an easier bomb to design. Mm-hmm. So,
in the book,
you
mention classical computing benefits from some virtual, this is one I didn't tell you about, benefits from some virtuous cycles in terms of speeding up. Is that still the case here with
So let's talk about virtuous cycles, right? So the virtuous circle is this idea from largely computing and silicon that the technology that you are building, you can then use to make the technology better, right? So our advances in semiconductor manufacturing and in computing in the 50s made it easier to build better machines in the 60s, which made it easier to build better machines. And we're still riding that virtuous circle of better and better classical machines.
It's a nanometer and beyond, right?
It is phenomenal that Apple is making consumer products with 3 nanometer feature size. Because like when I was in college, we were told that there would be tunneling, quantum tunneling, from one trace to the other trace. And it turns out like this 30 nanometers is 30 hydrogen atoms lined up next to each other. But apparently you still don't get, you still don't, actually it's 15, well, it's 15 or 30. You still don't get quantum tunneling even at that scale. But you know, are we going to get a virtuous circle with quantum? Maybe, right? So if we can use our quantum machines to simulate quantum physics and use that to build better quantum substrates, better quantum processors, yes. But it's much more limited than we saw with silicon.
So grab bag of things, workforce challenges, export control issues.
Yeah.
Can you talk about these things? These are sort of a little more esoteric.
Yeah, and so like the biggest workforce problem we have in this country is our immigration problem. You know, we don't have open borders. We don't make it easy for people who have technological skills to come to the U.S. and contribute to our economy. And that affects all aspects of technology. And until we address that problem, we're going to have very serious problems with workforce. And it's not just that, oh, we have to convince every single native-born American to study quantum computing. It's like there's a lot of other options in our society. And it would be better to draw from a worldwide population. They certainly want to come here. But in terms of getting people to pursue this, the people I know who are pursuing this don't think it's risky, but that's a selection bias. The people who think that it's a risky career choice aren't going into it. The quantum companies say that they can't hire enough people and that there just are not people who are qualified. Now, at the same time, it's going to get a lot easier to program quantum computers within the next 5 to 10 years. Right now, it's as if everybody who writes a quantum program is designing their own instruction set. And that's because these machines are so small that every possible feature in that machine has to be utilized. But when the machines get bigger, when they will hold superposition for a longer period of time, then what we're going to be able to have is a standardized instruction set. We're going to have better high-level languages, and it will be easier for people like me to write programs that run on quantum computers, should I want to do that, or to simply say, I want a quantum optimizer and drop it down. Now, that quantum optimizer is going to have to compete with the very best commercial optimizers. And if anybody here has not used a commercial optimizer, let me recommend that you look into this area. It's fascinating what's happened in the past 10 years. There's so much stuff that you might want to do that you can just have the optimizer do, and it's done. So the commercial optimizers are so good that many organizations won't need to move to a quantum optimizer.
Fascinating. So please line up at the mic if you have any questions. And maybe this is...
Oh, and my cough is asthma, so don't worry about it.
One final question. I understand the U.S. Congress recently passed the Quantum Computing Cybersecurity Preparedness Act. Can you talk about the relevance of that and what it does? This is the policy question for those who don't understand the physics.
So that was a surprise. Was this signed also?
You told me about it.
I told you about it. What did I say?
It was passed into law. I don't remember. I think it's a funding thing. But
oh yeah, the funding thing. Yeah, we're going to put more government money into it. It's great. No, the more government money we put into things, the better. That if you look at the amount of money that NSF has put into research, normalized against number of researchers, number of research institutions, number of competing priorities, just now we're at like a half to a third of where we were 20, 30 years ago. So anything, yes, that's a funding bill.
There is also a post-quantum preparedness element where agencies have
to
build some of that into what they're thinking.
Yeah,
like
so
quantum key exchange. And
I always have to be careful though, because I've had all these. I worked for the government until last August.
You can.
So right now, I can say anything here, right? So right now, there's a standardization process at NIST to come up with a post-quantum. A set of post-quantum algorithms, which are algorithms based on math that cannot be broken by Shor's algorithm. So not based on factoring, not based on elliptic curve, not based on discrete logs. Based on math that may not be as well vetted as factoring, which we have centuries of experience thinking about. One of the NIST proposals was found to be breakable shortly after it was published, but there are 4 candidate algorithms now. And what's going to happen is as soon as NIST decides on the final set of algorithms and the parameters to use them with, there's going to be this mad rush to sell new things to the government so that the government can immediately adopt these new algorithms. And it's just, there's so much money to be made selling things to the government. And one of the things that legislation says is that the government has to buy it. That we have to be, I
want to sell that.
I'm sorry?
I would like to sell that.
Yeah, there you go, right? So like if you've ever seen those PIV cards that have the smart cards and the chips, all of those have to be changed. They all have to have post-quantum cryptography algorithms in them. And the keys are like 10 times bigger, and they take more CPU power. And so it's just going to be huge amounts of your taxpayer dollars.
Buy Gemalto stock.
Yeah.
Thank you, Simpson, for
joining
joining us for
Thank
this.
you for inviting me.
Thank you so much.